Transformations are essentially functions. Let me take a function to start with. Here's one. We know that to be a function. And what this does is takes some stuff, in this case from the real numbers, and puts it into a different form in the real numbers. And we'll often write that as f colon real numbers arrow real numbers. What that means is we're going to take some things from the real numbers, do something to them defined by this function, and they're going to end up in the real numbers, perhaps in a different form. Well, transformations are kind of the same thing. We might have a transformation, for example, on, let's just go with an R2 vector here that would transform something that looked like that into something that looked like that's good enough. Something that looked like that. And in this case, what we're doing is we're going from R2 into R3. And so we write that transformation this way. Now, functions, and as we now know, transformations, have what we call a domain and a range. Here we have a domain and a range. And in fact, we know this other word now called codomain. So let's write these down and talk about them just to make sure we understand what the difference is. The domain, the range, and the codomain. Most of us are pretty familiar with the domain, and we at least know what the word range is, although it's hard to distinguish between these two. I mix them up all the time, to be honest. The domain of a function is the world from which we take the input values. So the domain of this function is all real numbers. The domain of a transformation is the world from which we take all the input vectors, whether they're vectors, real number vectors, or whether they're polynomials. Doesn't matter what the vector looks like. In this particular case, they're coming from real numbered vectors of dimension 2. That's the domain. It's where we get the input values or vectors. The range is the world in which the outputs live. So in the case of my function here, my domain is all real numbers, right? I can plug anything I want into for x. And my range is all the squared numbers. Now, you have to keep in mind that this is not just squared integers, right? If I'm taking all my numbers from the real numbers, then some of my outputs, for example, if my input is 0.1, then my output is going to be 0.01. And that's not a squared integer. That's not like a 4 or 9 or a 16, but it is still a squared number. There might be some numbers in the range that are not in the set of all real numbers. Let me use a different function as an example. Let's use the absolute value of x. Okay, my domain, the world from which my inputs come is the same, and the world into which they're going is still the same, but I have a different function now. If I take a number like 3, that's in the real numbers, I can take that number, and I plug it into my function, I'm going to get the absolute value of 3, which is 3. If I take a number, and so that's in the real numbers as well. If I take a number like -3 and plug it into my function, my answer is going to be +3. And that is also in the real numbers. But notice that the outputs are no longer going to contain all of the real numbers. It's only going to contain the positive real numbers and 0. So the range is where the outputs actually end up, the actual list of output values you get from the function. The codomain is just the world in which those answers live. So what I've written here actually is the domain and the codomain. I'm going to try and illustrate this with a slightly different approach here. I'm going to draw 2 circles. One is my domain, one is my codomain. This function takes numbers from the domain, does something to them, transforms them, and puts them into the codomain, or they end up in the codomain. That's where they live. So all of my inputs here are going to be real numbers, and all of my outputs are also going to be real numbers. So let's take a couple of examples. If I take -1, -3, 0, and 2, and use this function, use this transformation to map them, then I'm going to get +1, +3, 0, and 2. Well, the real numbers still has -1 and -3 in it, right? But we didn't use them. This is a subset of the codomain, and we call the subset the range. The range is the actual outputs we get when we do the transformation. I've run out of room again, as is typical for me, but I'm going to try to squeeze a graph in over here. The graph of this function looks something like this. And the reason for this is that if I take a value like 1, then when I take its absolute value, my output is also 1. But when I take an input value of -1, then my output value is also 1. Okay? What makes it a function is that for any particular input value, here's a 3, there's only one output value. Here's a different input value, -3. My graph doesn't go far enough. I'm going to change that to a -2, just so that I can get it in there. -2 goes to +2. +2 also goes to +2. Okay, so I'm mapping from 2 to 2. This 2 right here only has one output. It's 2. This -2 only has one output. It also happens to be 2, but it only has one output. That's what makes this a function. That's the formal definition for what makes it a function. The reason the vertical line test works on a function is that if I draw a vertical line anywhere on my function, it only crosses the x-axis. Sorry, it only crosses the graph once. The reason that tells me it's a function is that it aligns the one value of the function with its single value of, with its input, right? This input only has one output. So that makes this a function. Now, this isn't an algebra class, so I'm hoping that you already remember all of this. We need to talk about what it means to be a one-to-one function, which I hope you also still remember, and also what it means to be an onto function. And I'm talking about functions here because they are so closely related to linear transformations. A function has to meet certain criteria, right? It has to have only one output for every input. We could write that quite formally. We could say that to be a function, for every x in the domain of real numbers, there exists exactly one y equals f of x in the real numbers. And that's fancy mathematician speak for what I just said down here. For every x, there's only one y. For every x, that means for all, for every, or for each x in the domain, which is real numbers, there exists, or there is, exactly, that is an exclamation point. Where is my eraser? There it is. It's an exclamation point. Exactly one y, which is equal to f of x, in an element of the domain, the real numbers. So that's just kind of shorthand. That's what it means to be a function. But transformations have their own set of rules, right? In order to be a transformation, we have to have that t of u plus v is equal to t of u plus t of v and that T of A, I'll use R, T of RU is equal to R times T of U. Right? We have this definition of what it means to be a transformation. If we can meet those criteria, then we can move on. We can talk about other things. If we can meet the criteria of what it means to be a function, then we can talk about things like range. We can talk about things like domain and codomain and so on. But to get to that point, we have to be able to say that this is a function. Only a function can be a one-to-one function, for example, right? So we'll get to that vocabulary in just a minute. But the first criteria is that we meet those requirements, the requirements of a function in this case, and the requirements of being a transformation in this case. Now, it doesn't have to be a function to have a domain and a range and a codomain. It doesn't have to be a transformation necessarily to have a domain and a range. It can be a relation instead of a function. But the domain, the range, and the codomain are important concepts, and we'll see why that is in just a few more minutes, probably on another slide. Let me, with my function here, remind us that the domain, actually, I think what I'll do is write it down here. This is the domain for my function f, and that is all real numbers. I can pick any number I want, absolutely any number I want for my input, as long as it's real. And so I've got it on my map down here, I've got it, the circle labeled with the double struck R to indicate that the things in this set are all the real numbers. I've only picked a few kind of representative values here to work with, but what's actually in here, or what's supposed to be represented by being in here, is all the real numbers. No complex numbers, no imaginary numbers rather. There are some complex numbers in here actually. Here's one right here, 2 plus 0i, right? So the real numbers are also complex numbers, but they are not imaginary numbers. Okay, so there's my domain. The domain for this function f is all real numbers, and here it is represented here. The codomain is also all real numbers. All the real numbers are over here again. And so I'll write the codomain for this function f, and I'm only talking now about this function right here. That's the one for which I'm saying the domain and the codomain are all the real numbers. The range, however, is not all real numbers. It's only the numbers that I get out by squaring. Sorry, I'm not squaring anymore. It's only the numbers that I get out by taking the absolute value of an input. So the only possible outputs are all going to be positive, right? So I have all the positive real numbers. That's how we would notate that. But I also have 0. Now 0 is not positive. It's not neither positive nor negative. So I have to find a way to include it. What I've got here is a kind of set notation. So I'm going to say the set of all positive real numbers plus the set containing only the number 0. And that is how I would represent the range in this case. The range is a subset of the codomain. For my transformation, where am I here? My domain is all of R2. Okay. My codomain is all of R3. But my range is only the vectors in R3 that I can get by combining these two values in this particular way. So the codomain is all of R3 and the range is a subset of that. One way to maybe sort of help you think about this is that if you think about taking an input value, where is that going to spread to? Like, what is the range of these values, right? These values all go to here. That's its range. That's how far the inputs can range in their new environment. They can't range outside of that. The range is a smaller or a subset of the codomain. I don't know. Kind of helps me a little bit. Remember which one's which. All right, now I'm going to go to another slide because we're going to talk more about the idea of the domain and the codomain in a slightly different context. All right, now that we know what a function is and we know what a linear transformation is, I want to talk about the idea of being one-to-one. A function can be one-to-one or not, and a linear transformation can be one-to-one or not. And the idea is similar for both, so I'll stick with the function analogy for just now. This function is not one-to-one because there's more than one value in the domain that maps to a single value in the range. For example, there's a 1 in the set of all real numbers, and when I take the absolute value of that, it goes to 1. Let me use a different color here. Okay, 1 maps to 1 because the absolute value of 1 is 1. Negative 1, though, also maps to 1 because the absolute value of negative 1 is 1. Graphically, I'll put my graph of y equals the absolute value of x over here. That's where I have room for it this time. Okay. Graphically, if I take a 1 as my input, I get a 1 as my output. If I take a negative 1 as my input, I also get a 1 as my output. And as far as being a function is concerned, that's okay because I have one in for each input, I only have one output. Negative 1 does not also have an output here or down here. 1 does not also have an output up here. So it is a function, but it's not what we call a one-to-one function because there are two x values for which the single y value of 1 can be obtained. One way to look at that here, let's do a function that is one-to-one. Let's go with f of x equals x cubed. That function looks something like this. I didn't do a very good job there. Okay, that's still not perfect, but it'll do. I'm trying to describe what it means to be a one-to-one function. For this function, if I take a 1 as my input, I get a 1 as my scale is off here. I get a 1 as my output. If I take negative 1 as my input, I get a negative 1 as my output. It's different. Okay. This function is one-to-one because for every y value, I can only trace back to one x value. This function is not one-to-one because for every y value, I can trace back to more than one x value. Here, if I pick a y value, let's even go negative. If I pick a y value, the graph only, at this height, if you will, the graph only appears here and can be traced back to one x value. So this function is one-to-one. Here's a definition, and I'm going to change my function name so that because we already have an function f of x up here. So here's our function g of x. The idea of being one-to-one means that for every y in the real numbers, but in that case, that is my it's my codomain, but it's also going to be my range, as it turns out. For every y, there exists only or exactly one x. I forgot my 1. In the real numbers, there's exactly one x in the real numbers, such that when I plug it in, I get x cubed. Actually, maybe it would be even clearer if I did that. So now what it says is for every y in the real numbers, there's only one x in the real numbers that gives me that y when I plug it into the function. So that's what it means to be one-to-one. And a transformation can also be one-to-one if every vector x that you plug in, I don't remember what my actual transformation was. Let me go look it up. So here's my transformation. If it turns out that everything in the input world only maps to one thing in the output world, then that makes it a transformation. If everything in the output world can only be traced back to one thing in the input world, that makes it a one-to-one transformation. Now, here's the really good news. I'm going to draw a line here because above this line I'm talking about functions and below it I'm talking about transformations. let's draw the set of all of R2, that's my domain, and the set of all of R3, that's my codomain. My range may be something different. And let's see, here's my transformation. So I'm going from R2 to R3. And the question is, if I take something in R2 and use this transformation to map it into R3, it has to fall into the range. But once it gets there, let me just put a question mark here. Let's just say that, I don't want to circle it, too many circles going on here. Let's just say that this vector here maps to whatever this is right here. The question is, this thing right here, can it be traced back to something else? Is there another way to get to this thing here than just this vector here? And if the answer to that is yes, then this is not a one-to-one vector. If I go back up to this function here and take my output, which is the number 1, and I say, okay, I got there by taking the absolute value of 1. Is there another way to get here? And the answer is yes. I can trace it back to -1. That makes this not a one-to-one function. If I can trace this output back to more than one thing in my domain, then it's not a one-to-one transformation. The really good news here is that we know, for example, let me erase a couple of things here. I'm going to erase that, and I'm going to put in a y1, y2, y3, just so we have something in that space. I'm not going to go into the details here about why this is the case, but I know that the 0 vector is in the domain, and I can map to the 0 vector in the range. We talked about that before. That is, in fact, a property of linear transformations. And so the 0 vector is going to map to the 0 vector. That's great, right? That's not new information. The question is there anything else that maps back from the 0 vector? Let me put that in here as a dotted line. Could I have gotten here from some other input? Now, there might only be one place on a function where you take one output and can trace it back to 2 inputs, and that's enough for us to say, okay, it's not one-to-one. But if you pick a value on a function and you can only trace that value back to one input, that doesn't necessarily mean it is a one-to-one function. You need to keep checking, right? You need to keep testing values to find out whether there might be one out there which can be traced back to 2 input values. The good news with transformations is that that's not the case. If I take the 0 vector in the output in the range, and I can only trace it back to the 0 vector in the domain, then I know it's a one-to-one function. I don't need to test all the other ones. So we say that a linear transformation T is one-to-one if and only if, I like this abbreviation for that because it's very precise and concise, if the null space of T is exactly and only the set containing the 0 vector. The null space, remember, is all the vectors in the domain that map to the 0 vector. And what we're saying here is that if the only vector that maps to the 0 vector is the 0 vector, the set containing only the 0 vector, then that's enough. We can say that the linear transformation is one-to-one. Let's take a minute and see if our current transformation is one-to-one. I'm going to go do this on the next screen. And once we've talked about that, we have another vocabulary word to discuss as well. In order to find out whether a transformation is one-to-one, what we need to do is determine whether or not the 0 vector only maps back to the 0 vector. In other words, if the 0 vector in the range maps back to only maps back to the 0 vector in the domain, then it's one-to-one. So how do we find out? Well, we take our target vector, the zero vector, we need to know what that looks like. So we're going to take that vector and we're going to say that's what we want our answer to look like. So what we want here is for x1 plus x2, x1 minus x2, and 3x1. We want that vector to equal the zero vector. Well, that's just a system of linear equations, right? We have x1 plus x2 equals 0, x1 minus x2 equals 0, and 3x1 equals 0. Now, x1 and x2 represent all the possible combinations of two real numbers because we're coming here from R2. So the reason I'm using generalized values here is because I want to be as generic as possible. I want to determine what x1 and x2s there are in R2, right, in the real numbers, two combinations of two of them, because I'm in R2, which combinations and which numbers map to the zero vector. And my hope is that only 0, 0 will map to the zero vector because that will tell me that this transformation is 1 to 1. If I find anything other than 0 and 0, 0 for x1 and 0 for x2, the zero vector in this space, then it's not a 1 to 1 transformation. So let's keep going here. This third equation here tells me that x1 equals 0. The second equation tells me that x1 equals x2. And since x1 equals 0, x2 must also equal 0. And this third one here is kind of irrelevant. Now I know x1 and x2 both equal 0, so 0 plus 0 equals 0. That just confirms it, if anything. So my answer is that x1, x2 has to equal 0, has to give me the 0, or has to be the zero vector in the domain. Therefore, the transformation t is 1 to 1. Now, the key here in getting started was to recognizing what I wanted the zero vector in the range to look like, right? I started, the question is this 1 to 1? I started with the answer. The answer equals 0. And what did the question have to look like to make the answer equal 0? If I had had a free variable in this system, then I would have to have said that this was not a 1 to 1 transformation. But as it turned out, the only possible input, doing this little bit of algebra here, the only possible input that's going to spit out the zero vector is the zero vector. And the thing to remember here is that what this collection of vectors is, how do I say this? The set of all vectors, I'll say U in R2, and they look like this, such that the transformation of U equals the zero vector. That set, this collection of things right here, we call that the null space of T. So if the null space of T is equal to only the zero vector, the set that is the null space of this is a collection, this is a set, right? If the only thing in there is the zero vector, then we say that T is 1 to 1. Oops. 1. This is pretty powerful because this is the only output value we have to check. The only output value we have to check is the zero vector. If we can take the zero vector and map it back to the zero vector in the domain, zero vector in the range, and map it back to the zero vector in the domain, and we can't map it back to anything else, then we're done. T is 1 to 1. Okay, now we're back to our function again, f of x equals the absolute value of x, because we have another new vocabulary word to talk about here. If I can find a way to use up all of the codomain, this is the codomain. This is just the range, it's a subset. If I end up using all of the codomain, then I can say that the function is onto. In other words, we map all of the codomain onto, all of the domain onto all of the codomain. That's what it means to be onto. Clearly, well, clear to me, this function is not onto because I haven't used up all of the codomain. There are numbers in the codomain of the real numbers that didn't get mapped to, right? There's nothing in there's nothing in the domain that maps to -1. It doesn't happen because of what the function is, right? If I take a different function, let me move this up just a little bit. I'll put that here. And then I will introduce a different function, g of x equals x squared. It's going to have a similar problem, right? If the domain is all real numbers and the codomain is all real numbers, then I could take a -1 or a +1 here. Those will both map to 1. That's in the range, but -1 doesn't get used. So this is not not onto. Did I say 1-1 a minute ago? I meant onto, not onto. And this one is not onto. But our new favorite function, h of x equals x cubed, that one is onto. Because there's my domain, there's my codomain. The function is going to go from there to there. If I take a -1 and cube it, I get a -1. If I take a +1 and cube it, I get a +1. A -2 goes to -8. And if I want to use, say, a -3 here, then all I have to do, if I want to end up with a -3 here, then all I have to do is to plug in the cube root of -3, and that's allowable in this domain, right? The cube root of -3 is a real number. The square root of -3 is not. So that would not have worked, but the cube root of -3 is a valid real number. So I have taken all of the numbers in the in the domain, the real numbers, and mapped them using some tricks somehow, sometimes by taking the number in the codomain first and mapping it back. I can end up with all of the numbers in the codomain. And in that case, the codomain, oh, wrong color, the codomain equals the range. They're the same set. Everything in the codomain is included in the range. And when that happens, we say that the function is onto. So this function is onto. All right, let's use this information to see if we can figure out whether our transformation is onto. Okay, here's my transformation again. And my question is, let's do our diagram here. I'll do a bigger version of it. The domain is R2, and my codomain is R3, right? Vectors in the codomain, my output values, my output vectors are all 1, 2, 3-dimensional vectors. So my codomain is R3. My transformation takes things from R2, puts them into R3. So an input will look like this, and an output will look like this. And the question is, to determine whether it's onto, is there anything in the, let me do this. My output's going to look like this. Is there anything in the space out here? If there is, then this transformation is not onto. Another way to think about it would be to say, is there a vector here whose mapping, whose solution goes to some vector here that's not in my range? Well, pretty much that just means being really comfortable with what the vectors in the range look like. Let's see if we can write this a different way. If I say x1 plus x2, x1 minus x2, 3x1 can be written as 1, 1, 3 times x1 plus 1, negative 1, 0 times x2, then clearly I can choose any value I want for x1 and x2, and that's going to give me the answer in the range. But is there a vector out there that does not meet this criteria, but is still a vector in R3? So what I'm really looking for is a counterexample, and let's just see, let's let the vector b in R3 be equal to R3 be equal to 1, 2, 3. And so now I have an answer, and what I want to do is work back to the question to see, can I write this vector as this kind of linear combination? So that means we're essentially looking for a solution to a matrix equation that looks like this. My matrix A times my matrix X equals my matrix B. That ends up being possible. I've really starved myself of space. I've done a stellar job this time, above and beyond. Actually, I think I'll just get rid of all of this. I can do this using techniques we've learned before. If I take this 1, 1, 3, 1, negative 1, 0, and augment it with 1, 2, 3, and I reduce that matrix, I get this matrix. And at first glance, that looks really tempting to say, oh, look, you know, I have a nice square diagonal matrix. It's in reduced echelon form. These are all ones, therefore I'm good, right? But remember that this is an augmented matrix. What this is telling me, and I always like to look at the last row with an augment or with a reduced matrix, because this tells me the most, the fastest. This tells me that 0x1 plus 0x2 equals 1. In other words, the claim here is that 0 equals 1, and that is clearly not true. And so what that means is that this vector does not satisfy this transformation, and yet this was a vector in R3. So if I draw my transformation again in this form, I found this vector, 1, 2, 3, outside the range of the transformation, and therefore T is not onto. Okay, this video is already pretty excruciatingly long, but I'm going to do one more screen, and I'm going to use it to show you another example of how to find a null space in the null space of a linear transformation, because that's not something we really spent a lot of time on here. I've spent the time that I have talking about domains and ranges and codomains and functions and transformations and onto and one-to-one, so that we can ask ourselves those questions about transformations in the very near future, specifically in your topic assignment exercises. But I also want to spend just a little bit more time showing you how to find the null space of a transformation. Okay, in this case, I have a transformation T that's going from the domain of the polynomials of degree 2 or less and going into a vector space of R2. So I have two by one vectors, 2 by 1 matrices. And I want to find the null space of T. So again, the first thing I need to do is figure out what that null space looks like. The null space is all the things in the domain, all the things that look like this, that map to the zero vector. So what does the zero vector look like in the codomain? Looks like this. But we have to ask ourselves, where did that come from? It came from, in this particular case, because of this particular transformation that we're doing, this transformation spits out things that look like this. We have that a plus 3c and a minus c, those two components each equals 0. Each component is 0. So I can write that as a plus 3c equals 0 and a minus c equals 0. This equation tells me that a equals c. And if a equals c, let me highlight that because it's an important result. If a equals c, then I can plug either a or c. I just plug a back in there. Because a and c are equal, I can replace c with a. So now I have a plus 3a equals 0, or 4a equals 0, or a equals 0. That's another important result. I now know the value of one of my coefficients here. It's 0. I also know the value of my other coefficient, because if a is 0 and a or c are the same, then c must also be 0. And so I know that the value of this coefficient. So I have these important results and these important results. Those are both 0. So now I know what an input has to look like in order for me to get an output of all zeros. And that means that the null space of T is a subset of the domain that's made up of a x squared plus bx plus c, where a and c are both 0, and so that's just bx. So the null space of T is made up of all the vectors that look like this, where b is a real number.